Okay, then settle down. So we finished LU factorization this morning, and we're now going to complete Cholesky factorization. So this is a very nice method. It's actually a lot more efficient than Cholesky factorization. It's a lot more efficient than LU factorization. Now, this can only be applied to certain type of matrices. But if you have a matrix of this type, this is what you do. So you don't bother with LU factorization because this is so much quicker, but only a certain type. Okay, so we have seen that LU factorization factorizes a square matrix into the product of two other square matrices, L and U. L lower triangular, U upper triangular. Well, Cholesky factorization does similar, but this time it factorizes it into the product of L and L transpose. So you don't have an upper triangular matrix with LU. Well, you do have one, but it's simply the lower triangular matrix transposed. So, for example, if I have a 4x4 matrix A, which we have here, we want to factorize it into the product of the lower triangular matrix L and the transpose of L. Okay, so we don't have a U matrix. We're not bothering. We're only calculating L, and when we multiply L, we multiply L by L transpose. The difference with this L matrix as opposed to LU is the main diagonal elements don't have to be 1. Okay, well, they won't be. Well, actually, I can't say they won't be 1. They may be 1, but they don't have to be 1. Why would we want to do this? Well, calculating Cholesky factorization is quicker. We only have to bother with the lower triangular elements. We don't have to look at upper triangular elements. Unfortunately, we can't do this for every matrix. Only certain types of matrices can be factorized using Cholesky. These are called positive definite matrices. Okay, so that's what we're going to look at for the first part of this lecture. Okay, so a couple of quite formal theorems here. A square matrix A is positive definite if it is symmetric and X transpose times A times X is positive for any non-zero column vector X. Okay, that's quite a formal definition. We're not going to use that. Okay, I've given it to you because that's a formal definition of it. In practice, we don't use that. Okay. Another theorem is all eigenvalues of a positive definite matrix are positive. But that does not mean that if you have a square matrix, calculate its eigenvalues. If they're all positive, we have a positive definite matrix. That's not the case. That's okay. So these are just a couple of definitions and theorems which you should be aware of, but they're not that useful. What is useful, especially when we come to look at QR factorization in a few weeks, is given a non-singular matrix A, in other words, there exists an inverse of A, the matrix A transpose times A is positive definite. Okay, and there are a few nice proofs that go along with those. Sorry, Tom, can you just get the door, please? Sorry, thank you. Okay, I'm not going to go through the proofs here. I think I've sort of briefly written them down on page 110. Okay, so you can see there are some proofs there. What is more useful is something called Sylvester's criterion, which we'll look at in a minute. Sylvester's criterion uses what we call leading principal minors. All these is if you have a matrix A, a square matrix, a leading principal minor is the determinant of the first k rows and k columns. So, for example, here we have our matrix A. It's a 3x3. Okay, this has 3 leading minors. Okay, so leading principal minors, leading minors. These are the determinant of the first row, first column. So we can make a matrix which has one element, the element in the first row, first column of A, calculate its determinant, and the leading minors, first one is 1. If we take the first 2 rows and 2 columns, we have the matrix 1, 2, 4, 5. Okay, if we calculate the determinant of that matrix, we have -3. And finally, we have the determinant of the 3 by 3 matrix A. Okay, so that's the leading minor. Okay, so if we calculate the determinant, expand over the first row, okay, you did this back in the first year, and the determinant is 0. So leading minors are determinants. They just take the first row, first column, so take the first k rows and first k columns, form a square matrix, calculate its determinant. That gives you the leading minors. Okay. Why would we need that? Well, Sylvester's criterion states that a matrix A is positive definite if all of its leading principal minors are all positive. So whereas before I said we could have used this definition to give us, or to determine whether a matrix is positive definite, it's a lot easier just to use Sylvester's criterion. So all we do is calculate the determinants of all the matrices found by taking the first k rows and k columns, and if they're all positive, we have a positive definite matrix. So for example, here I have matrix A. Okay, so if I take the determinant of the matrix formed by taking first row, first column, determinant of 4, which is 4, that's positive. If I take the 2 by 2, the first 2 rows and 2 columns, I have this matrix. Okay, determinant is 11, which is positive. And finally, if I take all of the matrix itself, calculate the determinant, I get 10. And therefore, 10 is greater than 0, it's positive. So all of those principal minors are positive, therefore A is what we call positive definite. One thing you may notice about A is it's symmetric. Okay, so you can see if I was to sort of if I was to find the transpose of A, I would get A itself. Okay, so that's another feature, not a defining feature, but a feature of positive definite matrices. Okay, so the first thing we have to consider when looking at Cholesky factorization is our matrix positive definite? If it isn't, we can't continue. We'd have to use LU. If it is, we can then use Cholesky. For small matrices, let's say less than 3 rows and 3 columns, Cholesky factorization is quite simple. All we do is multiply L by L transpose, equate it to our matrix A, say, and solve for the individual elements of L. So for example, if I wanted to calculate Cholesky factorization of this 2 by 2, it's positive definite because the determinants, the principal minors are 4, and 40 minus 36, 4. So both of the principal minors are 4, both positive. Okay, the lower L matrix, the lower triangular matrix, has elements L11, L21, and L22. Well, if I transpose that and multiply it, reading across, I've got L11, L21. So don't be fooled about the subscript. These aren't the subscript of the matrix. They're just this matrix transposed, and L22. Okay, so what I do is I want to calculate these 3 values. L11 is first row, first column. So first row, first column of A is 4. And if I multiply first row by first column, I've got L11 squared. This element, L21, is 6, should be equal to L11 times L21. So if I just do matrix multiplication for that element there. And bottom right, second row, second column is 10, which is L21 times L21 plus L22 times L22. Okay, so I've got this system. It's not a linear system because we have some unknowns which are squared, but it's quite a simple system to solve. L11 is clearly 2. So if you've got L11 is 2, then L21 should be 3 because 2 times 3 is 6. Okay, L21 is 3, so therefore that's 9. So 10 is equal to 9 plus L22 squared, so therefore L22 must be 1. So this gives us this Cholesky factorisation. Okay, check it, multiply L by L transpose, you should get back to A. Okay, so that's the general method, dead easy. Okay, that's on a 2 by 2, kind of simple. Let's have a look at a 3 by 3. Okay, so going across to visualizer. By the way, I've already checked, this is positive definite. If you want to calculate the determinants, you can, but you'll have to trust me. Okay, so what we're looking for is we're looking for a lower triangular matrix like so. Okay, that matrix multiplied by the transpose of that matrix. So all I'm going to do is transpose this one and write it on the other side. So I've got L11, L21, L31, 0, L22, L32, 0, 0, L33. Okay, so that's what I've got to equate. I've got to solve for 6 values of L. And all I'm going to do is equate it to the A matrix. So the first one, L11. So I'm going to have 9 is going to be equal to L11 times itself plus 0 plus 0. So 9 is equal to L11 squared. Therefore, L11 must be 3. Okay. What about L21? So we've got 6 is equal to, well, L21 is second row on the left matrix, first column on the right is L11. So that's going to be L21 times L11 plus 0 plus 0. So that's going to be 3 times L21 equals 6. So therefore, L21 must be 2. And we keep going. Down to the next one. Go down to the third row, first column. We have 6 again. And that's going to be equal to L31 multiplied by L11 plus 0 plus 0. Okay, L11 was 3. So we've got 3 times L31 must equal 6. So L31 must be 2. So it's best to go down, because if you go down each column, you then have the L11, the one on the main diagonal. So the next one we got is we don't have to worry about this 6, okay, because that's just 0. We only deal with the lower triangular, the main diagonal and lower triangular. Okay, so next one we go on to 5. So 5 is second row, second column. So we have second row, second column. So it's L21 squared plus L22 squared. Okay, so L21 was 2. It's going to be 4 plus L22 squared. So 5 minus 4 is 1. So So L22 squared is 1, therefore L22 is 1. Okay. Next, we go down the column to 4. So 4 is second row, third column. So, sorry, third row, second column, sorry. So third row, second column. So I've got L31 times L21. Okay, and L32 times L22. Right, so 3-1 is 2. 2-1 was 1. So I've got 2 plus 3-2, which I'm trying to find out. And 2-2, which is 1. I'm just going to, yeah. Hang on, 2-1 was 2, wasn't it? 3-1 was 2, that's 4. Sorry about that. Okay, plus L32. Okay, so therefore L32 must be 0 because 4 is equal to 4 plus whatever L32 is. Okay, last one. Third row, third column is 13. So this time it's going to be L31 squared plus L32 squared plus L33 squared. Okay. When you've got elements on the main diagonal, you'll have something squared plus something squared, etc. L31 was 2, so that's going to be 4. L32, we've got L32 was 0. L33, we're trying to calculate. So 13 minus 4 is 9. So L33 squared is 9, therefore L33 is 3. Okay, so we've calculated all 6 elements. Put them together. What's our L matrix? Well, we know we've got zeros in the upper triangular part. Okay, L11 was 3. We've got 2, 2, 1, 0, and 3. And that's the Cholesky factorisation. If you want to check it, okay, calculate L times L transpose. Okay. Oops, sorry. So if you want to check it, just transpose L, multiply L by L transpose. So what we've got 3 times 3 is 9. 3 times 2 is 6. 3 times 2 is 6. 2 times 3 is 6. Well, because it's symmetric, we know when those two are 6, 6, those two are 6, 6. 2 times 2 plus 1 is 5. 2 times 2 plus 0 is 4. And 2 times 2 is 4, plus 9 is 13. So you know you got it right because you multiply them together, you get A. Dead easy. That's all very well and good. As soon as matrices get larger, it gets a bit clunky. Well, actually, as matrices get larger, we actually just use the same method. There's a pattern. I think you can see there's a pattern evolving in the subscripts of the L's. Okay, is everyone all right with that worked example? Okay, so like with LU factorization and LUP, we use Crout algorithm. Well, in this case, it's called the Cholesky Crout algorithm. It's simply, the derivation is simply following what we just done. So the elements on the main diagonal, square root of aij minus some number. Elements off the main diagonal is 1 over lijj times that. So it's quite similar to the LU factorization we did earlier. Okay, so let's have a look at the example. Here we've got a 3 by 3. Again, let's say it's positive definite. I've checked it and it is. Like with the Crout algorithm for LU, we go down each column at a time. Okay, so starting with the first column, j equals 1. If we look at the main diagonal, okay, if j is equal to 1, that summation is nothing. And we just got ajj, well, square root of ajj. Okay, so square root of a11 is 4. Okay, so we got our first element. As we go down, okay, we got 1 over the diagonal element, for 1 over L11 times A21. So that's a quarter of 12. Obviously, that's equal to 3. And if we go to L31, again, 1 over L11 times A31, a quarter of minus 4. That's obviously minus 1. So you proceed down each column, as we did with the LU Crout algorithm. Okay, when we go over to the second column, our summations come in now because j is equal to 2, so j minus 1 is 1. So we've got the square root of a22 minus L21 squared, which gives us 2. And below the main diagonal, we have 1 over the main diagonal element, L22. And again, you've got that summation coming in. So unlike the LU algorithms, the middle number is no longer the k number. Okay, it's the second number of each one of these is a k. So rather than 3112, which we had, we've now got 3121. Okay, keep carrying on as you do. So 32, and then L33 is the last diagonal element. Okay, and that gives you your Cholesky factorization. So that's your lower diagonal element. Again, always perform a check just to see if you got it right. Multiply it by itself, you should get back to your original matrix A. Okay, so again, more work for you to do, I'm afraid, and more writing down. Right, this is a 4 by 4, so it's kind of, I wouldn't attempt this using the algebraic method, which we looked at before. It's too much work. So in this one, we're going to use the Cholesky Crout algorithm. Okay, so as always, move down the columns. So start with j is equal to 1. And your main diagonal element is simply the square root of a11. Square root of 4 is obviously 2. Okay. As we go beneath the main diagonal, you then move to the second equation. So by second equation, I mean this equation. So this is one for the main diagonal. This is one which is off the main diagonal. Okay, so we have 1 over L11 times A21. So we've got 1/2 times minus 6, so that's minus 3. And L31 is the same thing, except we've got A31. Oh, we've got, and L41 is very similar. Okay, the first column, I have to calculate 4. Okay, I have to calculate 4, and these individual calculations are easier. But on the next column, I only have to calculate 3. On the next column, I only have to calculate those two, and then I've only got 1. So it's a triangular number, 4, 3, 2, 1. Okay, so that's the first column. The second column, okay, the main diagonal element is L22. So now we have the square root of A22 minus L21 squared. So A22 is 10. L21 was minus 3. So we have 10 minus 9. Square root of 10 minus 9 is obviously 1. So beneath the main diagonal, I've got L32. And that's 1 over L22 times A32 minus L31 times L21. So just be careful about the i's, j's, and k's with the summation. Okay, so it's Li, it's Lik times Ljk. Okay, so it's slightly different to the Lu Crout algorithms. Okay, so 1 over 1 is 1, so I'm not going to bother with that. A32 is minus 2. L31 was 2. And L21 was minus 3. So we've got minus 2, add 6 is 4. Okay, L42 this time, very similar. L41, L21. Okay. So 1 over 1 again, I'm not going to bother with that. A42 is minus 11. Minus L41 is 3. L21 was minus 3. It gives us minus 2. So that's the second column done. I only had to do 3 in that one. Okay, third column. Main diagonal element is L33. Square root of A33 minus L31 squared minus L32 squared. So what have we got? A33 is 29. L31 was 2, so minus 4. L32 was 4, so that's minus 16. So 29 minus 20 is 9. Root 9 is 3. By the way, you'll rarely have nice whole numbers like this. I mean, obviously, I've designed this example to be nice and easy. But it doesn't have to be. L43. So we've got 1 over L33 times A33 minus L41, L31 minus L42, L32. And this is just relating to those two equations, one for the main diagonal element, one for the beneath the main diagonal. Okay, so L33 was 3, so I've got 1/3. There. Yes, you're right, thank you. So what is A43? Minus 5 here. Oh, don't know why I've got a comma there. Minus 5 minus L41 is 3 times L31, which is 2, minus L42, which is minus 2, so that goes to plus, L32 is 4. So what have we got there? Minus 5, minus 13, minus 6, so it's minus 11, plus 8 is minus 3, divided by 3 is minus 1. Okay, so J is equal to 4. So this is just a main diagonal element, A44 minus A41 squared minus A42 squared minus, L42 squared minus L43 squared. So we've got 30. 4, 1 was 3, so that's minus 9. 4, 2 was minus 2, so that's minus 4. And 4, 3 was minus 1, so that's minus 1. So that's root 16, so that's 4. Okay, so it's fairly, like all these Crout algorithms, it's fairly sort of mechanical. Okay, so put it all together. If you've got room at the bottom. So the first column was 2, minus 3, 2, 3. Second column is 0, 1, 4, minus 2. Third column is 0, 0, 3, minus 1. And the fourth column, 0, 0, 0, 4. Okay, that's the Cholesky Crout algorithm. Just keep going down the columns, plug in your values, do a bit of number crunching, and nothing there should sort of give you any difficulty. Okay, how do we know we got it right? Well, you can multiply that 4 by 4 by itself, but remember in the exam you'll have computers in front of you. So have I got MATLAB open yet? Yeah. Okay, let's have a look at what MATLAB thinks it should be. So I'm just typing in the matrix. Okay. So MATLAB's got a nice little function called Chol, with Cholesky. Okay. Unfortunately, for some reason, MATLAB defaults to doing it in an upper triangular way, which, you know, it's weird that because we're calculating lower triangular elements. So if we go lower as an option, okay, and that should hopefully be what we've got. Okay, so MATLAB uses the Cholesky Crout algorithm, and that's what that's calculated as. So if we calculate L times L transpose, and press the enter key, you can see we've got back to our original matrix A. So that command there was just Chol for Cholesky. Right. Again, what's the point in doing all this? Well, at the end of the day, we're trying to solve linear systems. So there's no point in actually factorizing your coefficient matrix if you don't do anything with them. So solving a linear system using Cholesky factorization, very similar to LU. Well, we're solving the system AX equals B. Okay. Well, if we use Cholesky factorization, A is equal to L times L transpose. So if we replace A with L times L transpose, we get that equation. And as before, if we let y, the vector y, be L transpose times x, we can solve for y by solving Ly equals B by forward substitution. And then you transpose L and solve Lx equals y, or L transpose x equals y by a back substitution. So this method halves the amount of effort that the LU factorization is, because we've only got one matrix. We don't have to calculate both L and U. Okay, so let's have a look at this example. Here we've got a 3 by 3 system. I think this relates to a previous example. And we saw in a previous example, but our Cholesky factorization was this. Okay, so you first solve Ly equals B by forward substitution. So we have 72 divided by 4 is y1. Coefficient of y2 is 2, so we halve it, and we have 62 minus 3 times y1, and y3 is similar. So we solve for y using forward substitution, solve for x by using back substitution on the transpose of L. because we need an upper triangular matrix. And that gives you the answer. Not a lot I really can say about that. It's very simple. Okay, so here we got a bit of a beast of a system, 4 by 4, but we've just done this. We've just done this factorization, so it shouldn't be that difficult to calculate the solution. Okay, so that was our factorization. So we had this. This was our starting. Okay, so if we want to solve this system, we first solve Ly equals B. So L was calculated previously. Times by Y. So these are unknowns. And right-hand side vector is 40, minus 52, 93, and 69. Right, forward substitution. 2y1 is 40, so therefore y1 is 20. Okay, y2 is, well, the coefficient of y2 is 1, which makes it easier. So we've got minus 52 minus 3, so that's plus 3 times 20, gives us 8. Y3, well, the coefficient of y3 is 3, so we've got 1/3 of 93. Oh, was it 93? Yeah. 93 minus 2 times 20 minus 4 times 8. So we've got 2 times 20 is 40, 4 times 8 is 32, so that's 72, 93 minus 72, 21, divided by 3 is 7. And y4, we've got a quarter, 69, minus 3 times 20, plus 2 times 8, plus 1 times 7. Yeah, what have we got here? 69 minus 60 is 9. Add 16 is 25. Plus 7 is 32. Divide by 4 is 8. Okay, so that was forward substitution. So that was Ly equals B. Back substitution is L transpose X equals Y. Because we need an upper triangular matrix. We need to go backwards. So if we transpose L, so first column becomes the first row, etc. And X is our, well, what our solution is going to be. And Y was 20, 8, 7, and 8. Okay, so if we just solve using back substitution. So X4 is going to be 2. 8 divided by 4 is 2, obviously. X3, well, it's going to be a third of 7 plus 2. Which is obviously 3. X2 is going to be 8 plus 2 times 2 minus 4 times 3. What we got? So 8 plus 2 times 2 is 12, minus 12 is 0. And X1 is equal to a half, 20 minus 3 times 2. Okay, so that's 3 times X4 minus 2 times 3 plus 3 times 0. Yeah, it's just going to be 0. So what have we got? We've got 20 minus 6 is 14, minus another 6 is 8, divided by 2 is 4. And that's the solution. So remember, with these factorization methods, I could change the b vector, and I could still use the same factorization. So that's where they're really useful. Quite often in systems, the actual coefficient matrix doesn't change. It's only the right-hand side values that change. So I don't have to go through all the effort of calculating the factorization again. I just have to go through the forward and back substitution, which is fairly easy, just a summation. Okay, let's check I got the right answer. Never be satisfied. Beauty of algebra is we could always know if we bang on with the answer. Okay, so previously I had the coefficient matrix. So if I calculate, well, if I enter in the right-hand side vector, okay, and I'm just going to use the backslash operator. 4032. There's the solution. Okay, that's Cholesky factorization. A whole chapter of the notes done. It's one of those things. It's just have to really learn it. A couple of things to note. You've got to check whether your matrices are positive definite. That's dead easy to do. Okay, so we got a matrix A. Let's say det A. Or what you can do is list all the determinants of the. Okay, so those are all the determinants of or principal minors, sorry, of A. So loop through 4 rows. Okay, so this calculates the determinant of the first ith rows and ith columns. Okay, so determinant, first principal minor was 4. Then we had another 4, then we had 36, then we had 526. So that is a positive definite matrix. We know you can calculate determinants. We tested you that. We assessed you on that in year 1. So when you're in an exam, don't bother going through all this sort of matrix of cofactors and all that. Just use the MATLAB. Okay, as long as you say the determinants are, and then write them down.
Is that back to the top for that?
Sorry. Oh yeah. Sorry. Have I?
Yeah.
Yeah. Oh, that's no good, is it? Oh well. Sorry, which 116? I've lost my pages. Oh yeah. Oh right. So I have. Yeah. Sorry, I didn't. Oh yeah. So I didn't notice this, but on page 116, this is something I did last year. That's the Cholesky Crout algorithm. It's kind of rendered a bit superfluous because you've got one in MATLAB which does exactly the same thing. But that's the bare bone. That's the bones of it. That's like buying a car and taking the engine apart, so you can see what's in the actual method. Okay. Any questions regarding Cholesky then?
What was your backslash operator?
That's just a generic